Okay, welcome to Radiation in Life. This is our lecture on, well, a topic called Radiation in Life. And we've got a bunch of different materials, and we're going to go through and we're going to demonstrate to you the fact that there are these materials, and some of them, well, they're frankly pretty common, and they are radioactive. And we're going to do a basic introduction to radiation. And the very first thing, obviously, we need to know about is, well, where does radiation come from? It comes from atoms. And what are the constituents of atoms? Well, we've got protons, neutrons, and electrons. And typically, when you have an imbalance in the forces within the atom, this is often a result of the atom being radioactive. And there's an imbalance, the number of neutrons, there's an imbalance, the number of protons. And what's going to be happening is everything tries to get back down to an equilibrium state. It always tries to get to the lowest energy level possible. And radioactive decay is one of the mechanisms that allows for atoms to do this. So we take our basic building blocks of the atom, protons, neutrons, electrons, and we have to figure out what's going to happen with them. Well, radioactive decay, we're typically talking about a couple different types of radiation. We're talking about alpha radiation, beta radiation, gamma radiation, and neutrons. We're not going to be demonstrating any neutron products here. Neutrons are difficult to work with. We do have a research reactor on campus, as well as several different sources that can emit neutrons. But for the scope of this class, they're a little beyond what we want to work with because they're so difficult to control. They're difficult to control because, well, they have no magnetic field. You can't bend them, you can't contain them. They just travel until they bounce around and hit things and eventually get absorbed. So, but we'll back up a little bit. So starting with some of the radioactive sources that we'll be working with in the class, we have three primary sources that we work with. And once again, those are the alpha, beta, and gamma. And I'll start off with the alpha source. What we typically use is this material. This is polonium-210. And it's a small piece of metal that contains the actual polonium. And we'll take that source and move that away. These are all sources that I happen to have laid out on the desk alongside of me right now that we're going to kind of show you what type of radiations are emitted by them. So here, I'm going to take my source, and this is a Geiger counter. This is the Geiger counter. It's the simplest kind of counter that there is. When a radiation or particle deposits energy inside of the volume of the detector, it generates a pulse. Every time we get a pulse, we hear a crack right here coming on our screen. And it's a pretty simple device, and it works. This is our alpha emitting polonium-210. And you can see there are a few counts there. One of the reasons why we don't get a lot of counts is because, well, these are alpha particles. Alpha particles are massive. 2 protons, 2 neutrons, and no electrons. So they don't travel very far. I'm going to take a piece of paper and just stick that in between, and we have no difference in counts now. So we have a huge difference. There are no counts getting into the detector. None of the particles can get through a single piece of paper. So that's why when we deal with alpha particles, we're not really worried about putting it directly on my hand, for instance, like this. The alpha particles are hitting the first layer of dead skin in my body, which is about 10, 20 microns thick. Energy is not being deposited in live tissue in my body, so there's no biological harm from it. Now, obviously, if a piece of paper can shield that, we all have these in our homes. Smoke detector. And that's a relatively good-sized source. And, whoa, wait a minute. So everyone has a smoke detector in their home. You have at least one. You probably have 2 or 3 even. And we have these because we do risk-benefit. The risk-benefit analysis tells us that the risk of the radiation in here causing you any physiological harm is infinitesimally small compared to the risk of having a fire and not really knowing the fire is burning. So this saves lives. So that's an easy risk-benefit that we can perform. Another bit of risk-benefit. This is salt substitute. And if we take and there's a little bit of a difference in count rate there. It's So let me pour a little bit in my hand. I know this sounds risky. I'm pouring radioactive material in my hand right now. And I'm bringing it right up to the volume of the detector. And there's a small change, very small change. Now, this is, as you can see, saltless food. This is something that people put on their food. And as a matter of fact, I can even take and eat a little bit of this. It tastes terrible. I don't know why people would put this on their food. But anyways, this is basically potassium chloride, which is similar to sodium chloride, which is all salt is. So here is radioactive material that you can put on your food, you can eat, but we do risk-benefit. The risk from this is really tiny. It's not really going to bother us too much. So the next type of radiation that we'll look at is going to be beta radiation. And beta radiation is basically when a nucleus has a bunch of forces, strong forces in particular. Or is that a weak force? Actually, that's a weak force. Beta decay is a weak force. So basically, the nucleus, as I previously stated, tries to get back into its equilibrium state, into this lowest energy state possible. And sometimes when there aren't enough protons inside of a nucleus, a radioactive atom will say, you know what, if one of my neutrons turned into a proton, I'll be okay, and my energy level will be really low. And that, by definition, is what a beta decay is. It's when a proton or a neutron turns into a proton and then emits a little bit of energy. The reason it has to emit energy, and a little bit of mass too, in the form of an electron, is because there's a difference in the mass between a proton and a neutron. And that difference is just about exactly the mass of an electron. So it all works out. So here's a beta source that we have. This is strontium-90. You see it's quite a bit stronger. The previous source, the polonium source we actually had to have the bare metal exposed. In this case, there's no, you don't see the bare metal from this source because the strontium beta particles are energetic enough to get out of the thin piece of plastic here. But that said, pretty strong count right there. I'm going to put a thin piece of plastic over the top of it. Pretty much all of the particles, all the beta particles are being attenuated or caught up in just a relatively thin piece of plastic. So it doesn't take a lot of plastic. If we were to take a piece of lead, none of the beta particles are capable of penetrating through the lead. So that's not going to have any real impact on our count rate. So one of the other areas that we're going to look at in terms of the presentation is we need to know a couple of the units of radiological science. There's one unit that I'm sure you've all heard of. It's a Curie, and it's named after Marie and Pierre Curie, and it's 3.7 e to the 10th disintegrations per second. And one of their colleagues, not a true colleague, but he was a co-Nobel Prize winner, Henri Becquerel, has the other side of the spectrum. And if we have 1 decay per second, that's called 1 Becquerel. And by the way, the 1 Curie happens to be the number of disintegrations or decays that are produced in 1 gram of radium, which was one of the materials they did a lot of their work with. So if you have 1 gram of radium, you should be having 3.7 e to the 10th disintegrations per second. By the way, a Curie is a lot of radiation. And if we're talking about rules of thumb, the sources that I have here, these Czech sources, this is cobalt-60, these are 1 microcurie sources. So that's 1/1,000,000th of a Curie. So the amounts are rather they're starkly in contrast. These are good because we can have a response from detectors that's measurable and its characteristics follow between what the materials do. But there's no chance for any biological harm to come to the students or the instructors for that matter. So the next source that we'll be working with is something that you guys have probably all heard about, and I don't know if you could see that very well. This is cobalt-60, and it's a 0.1 microcurie source. Ooh, wait, that's strontium. It's cobalt-60. It's cobalt-60, and it has a 5.27-year half-life, which means every 5.27 years, half of the photons that are in here decay away. And when they decay away, they give off, well, actually give off 2 photons, 2 high-energy photons. So this material is used in a lot of medical applications. It's used in a lot of industrial applications just because of how it gives off its radiation. And this is that whole process of trying to get back down to ground levels. And this material tries to get back down to a ground level really quickly. And in order to do that, it has to release a lot of energy quickly. If we contrast that with, say, uranium, uranium has a 4.5 billion year half-life. It takes it a long time. It does a very slow process. And if we were to wait, say, a half-life for cobalt-60, half of it's gone. We'd have to wait 4.5 billion years for a half-life of uranium to go by. So that's not a very practical material to do this kind of work with. So we'll take our cobalt-60 and we'll see we're getting a reasonable amount of counts. And if we were to take our paper, what do you think is going to happen? We're going to put the paper in between. So what we're looking at here are gamma rays. And gamma rays, to differentiate between a gamma ray and an X-ray, it's where they're born from. You take a gamma ray, you take an X-ray, they're traveling down the road together. The only way you can tell the difference between the two is to know the origin of the 2 different photons. They can have exactly the same energy, but it all depends on where they came from. Gamma rays come from the decay of a nucleus. X-rays come from electrons. That's why when you go and get an X-ray at a hospital, basically they're shooting an electron beam at a target that's producing the X-rays. So here, we're going to see what happens when we try shielding our cobalt-60 with a piece of paper. Essentially, nothing. Well, work for a beta particle. Maybe it'll work for us. I'm not seeing really anything. You might see a little bit of attenuation with the cobalt-60 because there's also a beta decay. There's a weak beta decay associated with it. But there's really not a lot going to be happening here. And there's a lot to do with how gamma rays interact with matter. Gamma rays only interact with electrons. So there's 1 sheet of lead. Okay, we've knocked it down a little bit. Go 2 sheets of lead. We're knocking it down, but it's slowly going down. Even 3 sheets. And that has to do with the fact that it's a high-energy gamma ray that we're looking at here. So, as I mentioned, this is a very widely used industrial material. It's used in hospitals, so it has a lot of really good uses in terms of risk-benefit. If you ever had to get cancer therapy, it's potentially one of the mechanisms that could be used to deliver cancer treatment in terms of radiation to a tumor. But here, let's get to a few other materials that you might not even realize are radioactive. The first one is this. You see that yellow color? That yellow color is uranium. And someone decided to use uranium to glaze this glass. So actually, I'm not sure if it's a glazing on the surface or this might be a treatment through the whole process of the glass, judging by how it's looking. This is uranium glazing. This is stuff called Fiesta ware. And it's definitely really cool. It's hip. Come on, everyone's seen this awesome color. Well, how would you like to eat from that? Whoa! Counts are going out of sight. So, let's do some risk-benefit here. The first thing we have to ask is, can we get bowls that are cool colors that are not radioactive? And the answer to that is yes. So, there's no real benefit to this. The risk to this is also somewhat minimal, because the radioactive material is in the glazing. And the glazing is a ceramic that's been fired onto the surface of the pottery itself. So it doesn't readily come off. I'm rubbing my fingers on it. I'm not getting uranium deposited on my hand. You know, I'm not going to go lick my fingers now, obviously, because I've been handling lead. But this is no real chemical hazard from handling this. Radiologically speaking, you really shouldn't have it, but they sold these for years. They gave them away at drive-ins, and this was a big thing. You'd go to the drive-in, and every time you went, you'd get a plate to take home, to mom. Some of the other things that we also have that are radioactive might be something like this older watch. Whoa, wait a minute. People used to wear this thing 24/7? Yes, they did. But the upside of it is, you can see I just flipped it around, the user wasn't getting a lot of radiation. But everyone around, because the radiation only goes in one direction, goes out from the watch face, this person had some shielding in the form of the back steel cover of the watch. So any of the radiation going in this direction was absorbed, and he was safe. So tritium watches. We'll talk about tritium watches in class. We'll talk about what happened with tritium dial painters back in the 1917, 1920 time era. During World War I, people used to paint watch dials, and they made a lot of money doing it. Unfortunately, they got a lot of radiation that they picked up. They picked up dose from sticking the paintbrush to do the painting into their mouths with radium chloride on it. And unfortunately for them, they eventually had some serious medical problems based on having that much radiation in their bodies. There was even a time at the turn of the century, people were just discovering that radioactivity existed, and people thought it would be great because maybe by drinking radioactive materials, they would make them stronger and healthier. Unfortunately, it does not make you stronger. It does not make you healthier. There is no apparent medical benefit to drinking radioactive materials. But people did actually drink them. They had Radiathor and all of these wonderful products that were actually proved to be lethal for a few people because they basically decided they wanted to live off this radioactive energy drink. Picture Red Bull with radioactivity in it. It's kind of what it was, at least for its time. So, all right, what else do we have for radioactive materials? Well, some coatings that are used in metal and materials and space applications. This is a lanthanum-coated lens, and you can see there's quite a bit of radiation coming off of that. That's mostly beta radiation. There's one that is kind of, you're not going to see them as much anymore because they finally figured out a way to do this without having to use this particular material. And I don't know if anyone's ever been camping before, but we've seen our Coleman lanterns. And these lanterns basically take propane or they take white gas and they burn it and they heat up a mantle and then the mantle gives off light. It's called a Welsbach mantle. And, whoa, what's going on here? Okay, so this is your oldest style. And it turns out that the material that was used in the construction of this mantle is thorium oxide. And thorium gives off a really great light. Has anyone here ever, I'm sure you guys have heard of the term before, limelight. Limelight actually comes something from the time when they had this technology, and they'd heat up a piece of lime and they would actually be able to get a discharge out of it that produced white light. This was thermally before they actually had electrical incandescent lights. So thorium was used up until the late 1990s in these mantles. And if you were to take this material into a nuclear power plant, it would be really, really messy because they wouldn't know what to do with it. It would be considered radioactive waste the minute you walked in on site. So needless to say, they're here. We save them because it's a good demonstration piece. And the same thing in terms of risk-benefit. There's no real benefit to using thorium when you can use another rare earth material called cerium. And cerium oxide does effectively the same thing, same type of mantle, and there's no radioactive material used, so no one has to breathe this in. These break all the time if you've ever been camping and used one of them. And basically what you do when they break is you dump it on the ground and you put another one on because you need your light. But you didn't know it was radioactive. So, all right, let me check out and see what else we got. So one of the things we look at in terms of protecting ourselves from radiation is something called time, distance, and shielding. And they work together. We've seen the effect of shielding time it's kind of intuitive. The longer you're around a radioactive source, the more radiation is going to be absorbed in your body. Right? Okay. And then distance. The distance factor is one of the more important protection mechanisms, because the radiation given off by all of these sources that I have right here are going to behave as 1 over r squared in terms of how they drop off. And by dropping off as 1 over r squared, we just need to get a little bit of distance, and it's the square of that distance, the inverse square of that distance, that's going to protect us, because the radiation is going out equally in all angles, and just by moving further and further away, your body is going to present less of an angle and less of a view to the source of radiation. So I think that's about it in terms of our demonstration materials. Hopefully you'll remember that you do have radioactive materials like this in your house, and you can realize right away that they're there to protect you. If they weren't, we wouldn't have them. There are different kinds of detectors. Not all detectors use, not all smoke detectors use radioactive source, but they are best suited to detect approximately 95% of the fire types that occur in the United States. So it's a very effective mechanism for saving lives. Well, with that, I think we're at the end of our lab, and thank you very much.